be called mappy, but it really is called fmap. Says, give me a function from A to B, and something of type TA, some t, then I can turn it into a TB. So this is like things that can be mapped over. So we're abstracting over the type T, and we're saying there are things that we can kind of apply a function to everything in a second. I want to point out, before we do a bunch more examples, I wanted to point out an alternative way to think about this. So remember that function arrow is associates to the right, because a function that takes multiple arguments is the same as a function that takes a single argument and returns a function. Right? So we could look at this and we could say this is a two-argument function. It takes an A to B function and it takes a TA, and then it maps it and returns it to TB. But we could also think of it this way. It's the same thing, just maybe a slightly different way to think of it. That it takes a function from A to B and returns a function from TA to TB. So we could, an alternative way to think of it is kind of lifting a function from A to B up to work kind of in the world of, in the T world, whatever that is. So like if T is list, it takes a normal A to B function and kind of lifts it up to be a function on lists. Or if T is, maybe, it takes a normal function A to B and lifts it up to be a function that works on maybe. Fmap, right, so if f A to B, then I'll say fmap lifts normal functions into functions on keys. That is, if f is a function from A to B, then fmap f, or mappy f, is a function from TA to T. Does that make sense? Again, they're equivalent. Just sometimes one perspective can be more helpful than the other. So, if you actually have, let's say you have a list, and you're like, okay, what do I want to do with this list? I want to, apply a function to everything in the list. Fine, then you're thinking of it this way. You're thinking of, I'm giving it to a function and a list, and I'm going to get back the list that I want. But, maybe you're trying to construct kind of some pipeline of functions, or you just want a function that's going to transform a certain kind of list into another kind of list, right? And this might be the way you want to think of it. If I say fmap f, if I have a function from A's to B's, I can turn that into a function on T's. Okay. So we did some examples. We had lists, we had tree, we had rows, and we did maybe. Right, and I just wanted to point out that, like, you might look at these instances and be like, okay, so this is for things, where T is something that has lots of A's in it, and we're going to do this function to everything. Well, maybe it doesn't have lots of A's in it. It has 1 or 0. But it's still a useful idea that we can say, yeah, whether, I just want to say whether there's an A in there or not. Like apply this function to it. If it is there, you'll apply the function. If it's not there, then fine, it wasn't there, so we can't do anything. But it saves us from having to do the pattern matching ourselves. It just kind of handles both cases. And then we'll see some other examples in just a second that show that it's an even more broadly useful example, or broadly useful pattern than that. So here's what we're gonna do. I'm gonna write down a few different instances that we want, and I'm gonna put you in some little groups and see if you can come up with some code to implement. Okay. So the first one I want to do is this notation mean? So, so you know how you can write like, like 3 comma x as type, it's a pair of an int and a char, right? Of course. It turns out we can actually write that like this. So the comma in parentheses is just like just a special way to say I'm going to make a pair type. And what do you think the kind is of this thing? Type to type, yeah. It might say star, okay, yeah. It's using stars, but it's the same thing, right? So yeah, it takes 2 types as input and gives a type copy. So what does this mean when I write this? Just like a comma applied to some type. Well, we can partially apply these, just like we can partially apply functions. If I, say comma applied to int, like it's taken the first argument, but now it returns a function that's expecting the next thing, right? So the kind of this is star arrow star. And that makes sense because the thing we give to mappy has to be a star arrow star or a type arrow type thing, right? So just for this one, just to illustrate, I'm going to write down, so whoever gets this one is a little lucky, we're going to write down the type of this. So mappy, right, in general, it's going to have type A to B to TA to TB. Well, T, in this case, is this thing. So I'm just going to replace T with that, right? Which looks a little strange, but if you look at this, you say, okay, what is this doing? Really, I don't need these parentheses. It really means, the pair type constructor thing applied to E, applied to A. So this is really the same as, I'll leave this actually. I'll leave that there, but then I'm going to rewrite it in a more familiar way. So that is valid Haskell syntax, like this thing right here. But we can rewrite it to be more familiar. It just means this, right? So this thing makes a pair type, and we're applying it to E and A, so we can also write that. Right? And really, this thing here, this is just special notation for this. Like, this is really what's going on. Really, internally, there's a thing that you can apply to some types to get a pair type. And it just, Haskell provides some nice syntax for it. But, internally, once GHC parses everything and is like processing it, types, there's basic types like int and char and stuff, and then there's like types that can be applied to other types, and that's it. And then this is going to be similar, right? You can imagine that, what do you think this means? Yeah, this is the function from int to char, right? So just you can write this thing, the function arrow, we can write it in parentheses and put it. So it also starts there. Okay. So why don't 2B in the front row can do this one. Silas and Paxton, you guys can do this one, and then 3 of you in the back can try this. Okay. So I was, we'll start by writing down the type signature, and then see if we can implement a function that has the right type. Okay.
P, I
close.
think.
If I were you, I would have
So I
them
just
there
use-
instead of using first and second. Yeah, that was. Okay, no point.
So it's just a pair A and pair B this year. And then we pattern match like on P. So this is just pair. And this is just pair. And then the definition would be, or like the bottom part would be like mappy F BAA in parentheses equals,
Right, I don't know, maybe when it says arrow E, right, that's
so
that's
this
the question, right, arrow E.
right, it's a lot better than it's written.
E is actually
A to B. So pair
it looks like the arrow is
of A to pairs of B.
the arrow observes. Did you write down the type of what the map is?
F.
You should definitely, the first thing you should do is try to write down specifically what the type of map is, just kind of like we did in the comics.
How's about? We're getting there, I think.
Yeah, you can't name those the same thing. I mean, they have the same type.
Just call it A prime then.
Yeah, sure. Yeah, I think what you had before was too much. Well, I think it was correct, almost. I think maybe they were like
It's
just.
just P of FA of FA prime, like P, and then like parentheses of FA parentheses of FA. So, yeah, so it'd be something like, P, which I guess you don't really need parentheses on the outside. P of F. Type stuff up and maybe stuff I get like multiple but I have like pairs of one type, so I was like, yeah, yeah, yeah.
But the more I think about it, it doesn't mean like a letter after it.
Yeah, I guess it's because it's defined with one.
Yeah.
So you have to put one down there.
All right. Let's go to this. So, start with y'all. So, we've got this type pair, the single instructor P, two A's in it. So first of all, what was the type that you all said for the mapping would be?
Sure. It was a function of A to B, and then pair A to pair B.
Right. Yep, so we can just take, T with pair in this case. Good. And then, how did you implement that?
Basically, first you give f for the function, and then you give like the p of a to something, like a different, basically still a, but different name for a, and then you give it, and then that's equal to p of f of a, in that case, and f of a prime.
Okay, good. So yeah, we've got a p that has two a's in it, and we need to turn it into a pair b. So we need a p with two b's in it, and how do we do that? Well, we can just apply our function f to both things. Does that make sense? Make sense to everyone else? Okay. So how about y'all? We already wrote the type here. So how did you implement this?
So we start with f, and then in parentheses, we use different variable names. So I had e comma a.
Okay, yep.
And then we spit out in parentheses, e comma, and f a.
Right. Okay. Why do we not apply f to e? Yeah,
It doesn't change.
yeah, right. The e doesn't have to change. It doesn't change type. I mean, and it wouldn't. It would actually be a type error, right? Because f takes an input of type a, so e doesn't even have to. Yeah. So what's the difference between? I mean, these two are actually very similar, right? They're both pairs. Right. The difference is like. These pairs, both things in the pair have to have the same type, right? But in general, these kind of pairs can have different types. And so when you say it's a functor or a mappy, right, you have to kind of, there's only one type that you can change. So we can't change both at once. Turns out there's something else called bifunctor that's like for things that have two type arguments, and you can change both at the same time, but don't worry about it. So this, I would think of these pairs as representing like, yeah, I've got a pair of things. It's like a data structure that's got two things in it, of the same type. And so if I want to map, well, I can just apply the function of both. Makes sense. This, I think of it more like it's really a data structure that contains a single value that also has some extra information attached. And so when I do this, like the extra information isn't changing. It's just like the kind of main value that I'm applying a function to, and just leaving the extra information, just like it kind of comes along for the ride, right? Both potentially useful, just a little different. All right, how about this one? So, first of all, what did you all say is the type of mappy and for this instance?
We said it was a to b, e to a, e to b.
That?
Yes.
Okay. And how did you implement that?
So we had two functions, f and p, we applied, or we applied that to the function.
That's the output of G. What do you mean?
So we could also simplify that.
Oh, okay. Like that.
Yes, it's
Let's see. Take in type checks. Yep, type checks. Okay. Yeah. So right, this type signature actually, if you squint at it, it should look a little familiar. This is in fact the type of function composition. Just we're using E instead of like A, B, and C. But take a function from A to B and a function from E to A, and you chain them together. Like E goes to A, goes to B. So in fact, actually, this one, you can also just write this because it literally is function composition. Which is, I don't know, I find it really interesting that somehow this idea of mapping over something, it turns out that function composition is kind of an instance of that. And this, you know, if before we were thinking of this in terms of, you know, like all these instances, we were thinking in terms of data structures that had a lot of A's in them, you know. And like, I don't know, like these, are functions data structures? I mean, I'm not sure. I think there's a way to think of it that way, but not necessarily. One way you can think of it in terms of like data structures, think of a function from E to A. You can kind of think of it as it has a whole bunch of A's in it, and there's one A for every E, right? So, but instead of like literally having, you know, some kind of data structure, you can kind of ask for whichever A you want by telling it, like, oh, go look up the A that's, you know, at this E. Go look up the A that's at this E, right? Imagine if you had like an array, it's like an, if E is int, and it's like you tell it the index you want, and it looks it up, and it gives you the A in that index. So from that point of view, this kind of makes sense, right? If I had like, you know, an array of A's, you know, where, you know, I have some indices that can label the A's, I can map and turn it all into, you know, an array of B's indexed by the same thing. But obviously it's more general than that. They're not really arrays, they're functions. Okay. So let's think, what else can we make an instance for? Anyone think of any other types that we've talked about that maybe we could see if we could make an instance of mapping for those types?
Which ones have we done other than maybe before that one? Kind of forgot.
Okay.
But, I mean, I just didn't want to say the same one.
Right. Yeah, no, we've already done maybe, okay.
Yeah.
There's definitely some other types we've talked about before.
Look at this, yeah.
I mean, okay, so like we talked about like int. So would it make sense to make an instance of mappy for int? I guess I've given away the answer because it's underlining it in red. But why does this not make sense? Yeah, so it's one way we could say this, it's a kind error, right? Mappy things have to be things that have kind star to star, or type arrow type. So int doesn't take a type parameter. You can't say like int a, or, you know, int char, I know this makes sense. So, okay. So what are some other types we've talked about that have like some type parameters? Yeah.
Could use strings.
String. So does string have a type parameter? Like, can I say string A or like, you know, string int or something? Not really, because I can't do string either.
To map.
Map. Okay. So instance mappy map. Not in scope. I can give it. I can say m.map. So would this make sense? Yeah, so map, right, map takes two type arguments, the key type and the value type. So I can't just say mappy map, because that would be like, you know, it would be like A to B to, you know, map A to map B, but like map A by itself doesn't make sense. You have to say what the key type is and what the value type is. So what we can do is we could say something like this. So I've partially applied it to only the first type. So this is like maps with keys of type K, but I haven't specified what the value type is. So what would be the type of mappy in this case? So function A to B, and then what?
In map K. A.
I got map K, A. Why did I do that? about how maps work for a second, does this make sense? Do we think we can actually do this with a map? Or does it seem like a reasonable thing that you could do with a map? Yeah. Anyone want to argue no? Let's see. Maybe we could map. Map. There it is. There we go. There it is. Map. I mean, it's called map because, usually you import qualified, so you'd say like m.map, and it would know which map you want. I mean, it's also, if we look at actually the definition of the site, if we look down here at the instances, here it is. So it's an instance of Functor, right, as we would expect. So you could use, it provides a specific function map, but you can also just say fmap. I'm sure if we look at the source, it's just going to say, yeah, the definition of fmap is map. But this is like the map that's coming from. All right. So yes, that makes sense. So like we couldn't implement this ourselves because we don't know actually how map is defined, but it exists. We can use this. So. Okay, what else? Any other polymorphic types that we've talked about? I think of at least a few. So there's either. We could also talk about, I think we've used set. So which do you want to do? Set. Set. All right. So set does in fact take a, I have to import it, but it does in fact take a single type argument, right? I can have a set of whatever kind of values. Set S. So mappy would have type AB to S dot set A to S dot set. Okay. So, what do you think? Is this a reasonable thing to do with a set? A set of A's, and I'm going to apply a function to all the A's and get a set of B's. So, you're right, and also wrong. You're right that this seems like a reasonable thing to do with a set. But for a technical reason, this doesn't exist. So here's the reason. The way that sets are implemented is the elements are stored in like a balanced binary search tree kind of thing. Right? So they're kept in order so that you can quickly find something by searching in the tree. The problem is, right, that means it only works for things that have an instance of order. So if there's a way to compare them. If I don't have a way to compare A's, then I can't make a set A, right, because it relies on the ordering to put them in the tree. But this, right, mappy says, oh, if you have a set A and you pick any type B you want, and then you give me a function from A to B, then I could make a set B. But actually, you can't quite promise that because you can't make a set B for any type you want. You can only make it for types B that have an order that can be compared. Okay. So this actually does not exist since we can't make a set B for any type B, only for types that search for this, so if I search for A or B or set A or set B, there is a map function, right? But notice it's got this extra constraint. It says, so this, you can do this as long as B is ordered, right? Yeah, it's worth, this is a good note. You might not think about it. It's worth noting the size of the result may be smaller, right? Basically, if the function you give it is not injective, if there's multiple A's that it maps to the same B, you're going to get a smaller set out, but that's okay. There's also a map monotonic that doesn't have an OR B. So how does this work? Well, basically it says, yeah, this only works if you can guarantee that this function like preserves the order. So like if the A's are in order, then the B's will also be in order. And it doesn't check. It just like takes the tree and it just like does a map over it. And if you screw up and you give it a function that like the B's end up in the wrong order, it's just like your set is just broken. It's not like lookup and stuff isn't going to work. So it's like it's more efficient. So you can do this if you're really sure. But it definitely is not suitable to provide as like a generic instance of fmap.
So that's like generally saying like you know that the B's are going to be in order, so you don't have to technically write it, but you have to make sure that that's the case to use that.
Yeah, if you're going to use this, then you better make sure that this function you give it has the property that, you know, if you have two A's that are in a certain order and you call the function on both, the B's that come out are going to be in the same order. You know, so for example, if you were going to, you know, if you had a bunch of characters and you were going to turn each character into its, you know, into like its ASCII code, that would be fine because, you know, whatever order the character's in, it's the same order as their ASCII code. But if you did something like you have a bunch of integers and you're going to square them, that's no good because now, like, you could have -5 and 3 are in one order, you square them and then they switch for you. It's an interesting example where most things in the Haskell standard library, right? Haskell generally has the kind of the philosophy that like the type should give you pretty strong guarantees about what it does, and if you look at the type, you're like, as long as I call it with the right arguments, like the things of the right type, it's gonna work. It's not gonna crash. It's gonna give me the right thing. Right? This is an interesting example where we've made a trade-off and said, well, in order to get something that's more efficient, there's actually something about this that you can't just look at the type. But looking at the type is not enough. There's some extra stuff that you have to be sure that you're using it correctly. Otherwise, it's not going to work. I mean, it's not going to crash. It just might give you a set where the internal invariants of that data structure are not satisfied anymore, and so like who knows what the heck the set functions are going to do. If you try to insert something or like ask if something is in there, it might say no, this isn't in there, even though it was because it was in the wrong place. Someone raised their hand. I thought I saw someone raising their hand out of the car line. All right, so set doesn't work, but it kind of does. How about either? So again, either is type to type to type. So I can't just say mappy either. I would have to say like mappy either E. We can write this one together. So what's the type of mappy going to be here? A to B, 2. Okay, how should I implement this? Mappy F. Okay, yeah, so it could be a right containing an A. So this is a either EA. And then, what did you say? Do right FA, yeah. So I want to write, and I can apply my function F to the A to get a B. Okay, and what if it's the left? this is actually very similar to the maybe instance, right? The maybe instance said, if it's nothing, we're just going to keep it nothing. But if it's just, then we can apply the function to the thing in there, change its type. So here, we're saying, well, if it's a left, we're just going to leave it alone. But if it's a right, we're going to apply the function to it. So either, I mean, notionally, you look at either, and it's symmetric, right? It's like there's left, there's right. There's no particular reason to like prefer one over the other. But just the way that this works, because we have to choose one of the arguments to be the one that we're mapping over, and either is often used this way, where left signals some kind of error, and right signals, you know, a successful result. And so, just like maybe can signal that, right? But maybe, if you have nothing, it just says, basically means there was an error, there's nothing. Whereas if you have an either EA, if there's some kind of error, it can actually carry some information about maybe what the error was or something like that. So you can imagine, like, if you have an either string int, it's like, well, either you get an int if it's successful, or if it's not successful, maybe you get like a message telling you what went wrong. And this basically says, you know, if it was successful, then here's the next thing I want to do with this value. I'm going to do some more computation to it. But if it was not successful, that just kind of propagates, and you just carry along the error. So that's often useful. Think if there's anything else. Data.tree is basically the same as our rows trees. Right, it's got an A and it's got a list of trees. And of course, it has a functor instance right here. I haven't seen data.sequence. Data.sequence is very cool. It's very nice. Also, it's functor. Okay, anyway. In the few minutes we have left, I'm going to do one more example. So at this point, you might wonder, like, you know, if I have something that's a type arrow type, can I always make it match everything? So let's see. Let's make data. So here is a data type I made up called B. It just has a single constructor C that contains a function of type A to int. Okay. And let's think about what happens if we try to make this map. Let's say instance mappy B. So mappy would have type A to B to B A to B B. B is not a good whatever. All right, let's try to implement this. Well, I have my function f. I can pattern match on the b that I have, right? So I'll say c, and we'll call this g. This underscore. And let's think about the types of things that we have. So ideally, if this were agda, we could just do like control C, control comma, and it would tell us. Be like, oh, f has this type, g has this type. We could do it ourselves. So f has type a to b. What type does G have?
A to int.
A to int, right. Because it was inside of a BA, so it's this A. And then what type do we want as output here? Yeah, well, we want a BB, I guess, right? We want a BB. So we can actually say, all right, well, to get a BB, the only way I can do that is by using the C constructor. So I can, like, refine that and say See, and now it's telling us, right, the whole has type b to int. So now we want b to int. All right, so let's look at these. I want a function that turns b's into ints, but I don't know what b is. So the only thing I can do with b's is like whatever I'm given to use. But the problem is, if I try to make a function of type b to int, I could take in a b as input, and then what can I do with it? Nothing, right? All I have is I have these two functions that both take a's, and I'm stuck, right? I mean, this function can give me a b. I don't even have an a that I could give to this function to get a b, so I can't even get a b that way. But even that wouldn't help me, because I already have a b. I want to turn it into an int. This function will give me an int, but I don't have an a to give it. Like, I'm just totally stuck, right? This can't work. Totally stuck. Impossible. I mean, it's not impossible, I guess, because I could say, all right, I'm gonna make the function here that ignores the b and returns 5. But it turns out that's not a very good solution, because it doesn't take into account f or g at all, which seems kind of stupid. Like, what's the point? If I just want a function that always returns 5, I can just make that. I don't need to make a map. Say impossible, other than easy. 5. And if I didn't, that only works because I had int here. What if I put like, a? What if I had a arrow a? Right? Then I would really be completely, totally 100% stuck. So this is not possible. The problem kind of intuitively is the fact that the a here is kind of on the left of an arrow. It's like an input instead of an output. It only works if you have a's that are kind of outputs, or that are actually just contained in the structure. If you have a's that are inputs, you can't like change them into b's. Anyway.
Kind of makes sense, because it's kind of how we work with the 3 types.
Right.
You always have to match to the first